This one's just a quick video to talk about doing vector proofs and maybe some useful properties to remember for this. Now, when it comes to vector proofs, if you recall doing these back in Unit 1, then what you might remember is that as soon as you sort of feel like you understand how to do one proof, it feels like often the next proof question is asking you to conceptually sort of do something different. And it's not just vector proof, it's other proof that can be a bit like that as well. So unfortunately, it's very hard to say, well, here is how you do vector proof, because often each one will be a little bit different. But what we can do is talk about some results or some properties that might be useful to us. So we need to, we've done this for two-dimensional vectors. We're going to extend it now so that we can sometimes do three-dimensional vector proofs as well. Okay, so what are some properties? Firstly, regarding the scalar product or the dot product. And probably this first one is one of the most vital, and that is to remember that if two vectors are perpendicular, then it follows that their dot product is equal to 0. Or, alternatively, and maybe this is more common, to show that two vectors are perpendicular, we need to show this. In other words, if this is true, it implies that the two vectors are perpendicular. So anytime in a proof you're trying to prove something about perpendicularity, we'll generally be trying to show that the dot product is equal to 0. Alright, next one, just a reminder that the dot product of any vector with itself is just the square of its own magnitude. Alright, some couple of results or properties to do with parallel vectors or collinearity. We've considered these pretty recently. Firstly, if two vectors are parallel, so obviously here we're talking about non-zero vectors, and I guess in all these cases we're talking about non-zero vectors. So if two vectors are perpendicular, it implies that one can be written as a scalar multiple of the other, where k is any real number apart from 0. Likewise, if we can write one vector as a scalar multiple of another, it implies in the other direction that the two vectors are parallel. So a way of showing that two vectors are parallel is getting to a point where we can write one as a scalar multiple of the other. And then a slight extension or refinement or restriction on that is that if we can show that the vector joining points A and B is a scalar multiple of the vector joining points A and C, that in fact means all 3 points lie on the same line, the reason being that they share a point in common. So we've got parallel vectors where the two vectors share a point in common. That means the points are in fact collinear. And again, that implication works in both directions. Finally, just one other result, and this is if we have two vectors which we know are not parallel, so non-parallel A and B, if we have the result that some scalar times A plus a scalar times B, so a linear combination of A and B is equal to another linear combination of A and B, then it follows that this M has to equal P and N has to equal Q. So that's what this statement here is saying. Now we actually use that one all the time with I's and J's. So, an example of that one would be if we said 3I plus NJ is equal to PI plus 5J. Then we would say, well, we can see from that in fact P has to equal 3 and N has to equal 5. But it's not only true for I's and J's and K's, it's true for any vectors A and B and C and so on. So again, that might be a useful one when we're trying to sort of prove results if we can use those linear combinations. Alright, that's it for useful results and properties for vector proofs.